Welcome to our last episode of Electrostatics, and it might be a little bit longer than the rest. And in this episode, we are looking at electric potential. Electric potential is the work done in moving a positive 1 coulomb charge from infinity to a point in an electric field. To a point in an electric field. Infinity means moving the charge from very far in regards to charges is the charge is coming from a point which is far away that it is almost not affected by the electric field when it is still at that very far point. So if you bring it from that far point, a positive 1 coulomb, and you are able to move it to a distance, say x, from a known charge, positive 2, then the work done in doing that is what we call electric potential at that point. The expression of electric potential we are going to consider a positive 1 coulomb charge, which is x, positive 1 coulomb charge, which is a distance x from a positive charge q, and it is being moved from point C to point B through a small distance delta x. This delta x is small, just magnified for clarity as we are trying to derive, without significantly affecting the electric field due to positive Q. Now, while at point C, the force on that positive 1 coulomb charge is given by the force, of course, as we saw before, the coulombic force is supposed to be F is equal to Q1, Q2 out of 4 pi epsilon naught R squared. But in this case, I'm trying to use air or a vacuum, but if we use any other medium, it is simply epsilon, where epsilon is the derivative of that. Now, in this case, we have the first charge Q1 is positive Q, and now we'll use the positive in the formula. The other charge that we are trying to move towards positive Q is positive 1 coulomb. So times 1 out of 4 pi epsilon R squared. So we end up getting F is a Q over 4 pi epsilon naught R squared. Now, as you're trying to move the positive 1 coulomb towards the positive 2 charge, automatically these are all positive charges, so they are similar charges, and that means they will repel one another. So you're doing work against the field. So if you're doing work against the field, then the work done will be, of course, the force times moving it through a small distance delta x will be negative. The negative signifies that this work is being done against the electric field. So if we move, of course, we have to move through those small distances delta x, and as you move cumulatively from C to B, then automatically you would have moved a summation, you would have made a summation of work. Some significant work is done. So we are going to sum up the small work done, and in summing up, we use integration. So the total work done will be the integral sum from infinity to a point, a distance r from a given point charge. So we are summing up the work done. So work done, integral from infinity to R of negative Q dx over 4 pi epsilon x squared. Now, these are all constants. These are all constant and they are pushed outside the integral. So we shall remain with the work done is equal to negative 2 out of 4 pi epsilon integral of 1 over x squared dx. Now integral of 1 over x squared gives us negative 1 over x. Gives negative 1 over x, then the limits are from infinity to r. So putting back the limits, we get this expression, and that is when we substitute in the limits, we get 1 over r minus negative 1 over infinity. Now infinity being very far, it means 1 out of infinity is like picking 1 grain of millet or grain or sugar from a sack. Actually, 1 out of something very big is approximately 0. If you pick 1 bean from a sack of beans, you might even not realize that you have missed a bean from the sack. That means 1 item out of very many or very big or infinity is actually 0. So when we put 1 over infinity as 0, we end up with expression potential difference, no, electric potential, the Q over 4 pi epsilon naught R if it is in a vacuum or in air, and epsilon R if it is in any other medium of conductivity epsilon. So potential, electric potential is given by Q over 4 pi epsilon R, where Q is the charge, quantity of charge, and R is the distance of the point where we want to find electric potential from the charge that we are considering. Note very carefully that electric potential is a scalar quantity, and therefore, unlike the electrostatic force and the electric field intensity, we shall not be having to require, we shall not be required to find the modulus and the direction of electric potential. We shall simply add up the electric potentials due to different charges if it's a system of charges. Also, we shall observe that when it comes to electric potential, we shall be substituting the charges with their signs. If it's a positive charge, we use a positive. We put the positive in the formula. If it's a negative charge, we substitute it as a negative value. We have some examples here. Example number 1. A hollow conductor of diameter 21.4 centimeters carries a charge of 6.9 exponential negative 10 coulombs and is raised to a potential of 50 volts. Find the permittivity of the surrounding area. From electric potential is Q of 4 pi epsilon R. We now want permittivity epsilon, and it is, if we make it subject, it becomes Q over 4 pi VR. Now we have diameter 1.4. So to get the radius, here we assume that all the charge is concentrated at the center of the sphere. So distance from the center of the sphere is radius of the sphere. So for distance r, we are using the radius of the sphere. So since the diameter is 1.4, that means radius is diameter divided by 2, which gives us 10.7 centimeters, which we shall convert to meters as 10.7 times 10 to the power negative 2. So when we substitute in the expression, we get our epsilon, or permittivity of the medium, as 1.026 times 10 to the power negative 11 farads per meter. Number 2, find the electric potential, find the electric potential at P. Now at P, we only have one charge which is causing The electric potential and the charges at A is 10 microcoulombs or 10 times 10 to the negative 6 using the formula. Electric potential is Q out of 4 pi epsilon naught R. We substitute the values. 1 out of 4 pi epsilon naught is 9 times 10 power 9. The charge Q is 10 times 10 power negative 6 divided by distance in meters of 0.1 meter, and we get 9 times 10 power 5 volts. Find the potential at B, number 3. Find the potential at B. We have a charge at A of negative 5 microcoulomb, and point B is 20 centimeters from point A. Still, we are substituting. Note that now we are substituting in the value of the charge with its sign. Now it is negative, and the answer is negative potential, which is negative 2.25 times 10 power 5 volts. Which means now, when you are bringing this charge from infinity, since our charge is positive 1 coulomb, bringing it from infinity to point B, if you, based on how we define electric potential, you discover that instead of you doing work against the field will be doing work on you by pulling the charge that you're trying to bring closer. So since the electric field is doing work on you, not you doing the work against the electric field, we end up with a negative electric potential. Number 5, find the potential at point B. Now point B is being affected by two charges, a charge at A, a charge at B. So since we said the scalar sum, we shall just have to find the electric potential due to the charge at A. Then we find the electric potential due to the charge at B, and then we add them up. So VA would have been charged at A over 4 pi epsilon naught RA. The same thing with the VB, QB out of 4 pi epsilon naught RB. Now when we add these two, we realize that 1 over 4 pi epsilon naught is common, so we pull it out, is here. And since each of the charges also has a micro, which takes them for negative 6, has also been pulled out. And what has remained inside the brackets, we have worked it out, and the answer is 1.35 times 10 to 6 volts. Make sure that you do this step by step so that you can be able to follow very well. Potential due to hollow charged sphere. Now outside the sphere, the potential follows the formulas we have got it, but remember the charge Q and the 1 over 4 pi epsilon naught is a constant, so it means basically V is equal to K over R. Since K is a constant, we can say that V is proportional to R, but in an inverse manner. So since we have an inverse proportion outside the sphere, you expect to have a graph like this one, which shows inverse proportion. Then inside the sphere, since no charge resides there, the electric field intensity is 0, and therefore there is no work done moving the charge inside the sphere. So we have, since there is no work done there, that means all the points are at the same potential. That's why you see here inside the sphere, there is a constant potential. So the electric potential inside the sphere is a constant at V, and it begins reducing as you move away from the charged sphere. Electric potential difference between any 2 points is the work done in transferring 1 coulomb of charge from one point to another against the electric field. For electric potential, we're looking at moving from infinity to a point in an electric field. But now for electric potential difference, we are considering 2 points nearby a positive charge Q. So let's consider 2 points. You have a charge Q, an electric field. Then you have 2 points A and B. Point A is a distance small a from positive Q, and point B is a distance B from the point Q. Now, the force on 1 coulomb charge, because our aim is to move a positive 1 coulomb charge from B, from point A and take it to point B. Of course, since it is positive 1 and we have positive 2 here, we shall be doing that one against the electric field. So as we are doing so, we want to see how the work done will come out from there. Let us begin by considering 1 coulomb charge, which is at, of course, in our final expression, we shall be seeing we can get the electric potential at A, we get the electric potential at B, and we subtract them. It also works that way. Alternatively, we can now just integrate the work done directly in moving a charge from point A to point B. Let's consider 2 points A and B. Point A is a distance A from positive 2, and point B is a distance B from positive 2. Positive 2 is a charge. Now, the force on a 1 coulomb charge, assuming it's a distance x from Q, if you have a Q here and you have a positive 1 microcoulomb, these ones will have, so the positive 1 coulomb, these ones will have a force between them which is repulsive, and the force will be Q1, Q2. Q1 is Q, Q2 is 1 out of 4 pi epsilon naught. If you have, or let's use epsilon for the case of apply for any medium, and between these two charges you have a distance x. That is the formula for the force between the two charges, one positive, two the other 1 coulomb, a distance x apart. Now, if you move the charge, the positive 1 charge, a distance delta x, small distance delta x, against the electric field. This is against the work done, the small work done will be negative F delta x. Negative F delta x. That is a small work done. But if you are to move all the way from point A to point B, so you're moving through small changes, but which have now been integrated or added together, we shall say work done now is integral from A to B of negative F dx. And F is, we have the value of F there, we substitute. When we substitute it, we shall have work done is negative Q out of 4 pi epsilon x squared. We take out the constants, we have negative Q out of 4 pi epsilon naught integral 1 over x squared dx. And now we're integrating from where to where? From A to B. Those are our limits. From A to B. Now, when we integrate this, yes, already has some error here. We shall get integrating 1 over x squared, get negative 1 over x. Still we're integrating from A to B. Now, when we put back our limits, we get negative 1 over B minus negative 1 over A, and it comes to this one as our potential difference between the points A and B. Now, however, I encourage people to always look for electric potential at the different points, then they subtract, especially in view that sometimes we have negative values which might confuse us when we try to substitute them directly into the formula. We look at the examples Example 1, consider 2 points A and B at distance 15 centimeters and 20 centimeters respectively from a point charge of 6 microcoulomb as shown below. Find the potential difference between A and B. Now, we shall first look at the electric potential at A, electric potential at B, using what we've just looked at. Electric potential at A is 3.6 times 10 power 5 volts. Electric potential at B is 2.70 times 10 power negative 5. We want to look at the potential difference between A and B, so we shall subtract. So PD between A and B is the electric potential at A, take away electric potential at B. So you substitute and you get the electric potential difference as 9.0 times 10 power 4 volts. Now, part B, find the energy required to bring a charge of positive 1 microcoulomb from infinity to point A. If you recall the definition of electric potential, we're looking at a positive 1 coulomb charge from infinity to point A. That was the work done. So also here, the energy required to bring a charge of 1 microcoulomb from infinity to any point, we shall just multiply work done. To bring a charge from infinity to a point is actually the potential energy of the charge at that point. Now, potential energy is given by the work done in moving from infinity to a point A, and is always given by the charge Q at A times the electric potential at A. So, in this case, you're moving a charge of positive 1 microcoulomb. So, in the place of Q, we shall substitute 1 times 10 power negative 6. The electric potential at A, it was found as 3.6 times 10 power 5. We substitute and get the answer 0.36 joules. So energy and work is in joules. Here, note carefully that electric potential, we have got it. If at point A, we have electric potential at A. Now, the work done in bringing a charge from infinity to that point, a charge of any magnitude, is if it is a charge of one or 41 coulomb, it will be that potential itself. But if it is in any other charge Q, to bring it from infinity to A, is the potential energy at A, which will be that charge you have brought times the electric potential at A. Question number 2. Consider 2-point charges, 9.8 microcoulomb and negative 6.4 microcoulomb placed as in the figure below, in air as in the figure below. So if it is in air, we shall use epsilon naught, permittivity of free space. Find the potential energy of a charge of 2.5 microcoulomb placed at P. We have said potential energy is given by, just said, potential energy is given by QV. So PE at P is the charge you're placing at P times the potential at P. Now, what the potential at P? Potential at P is due to two charges. So we shall first find the potential at P due to the charge of 9.8 microcoulomb. And the answer is that one. How? We have to get the straight distance between P and Q using Pythagoras theorem is 10 centimeters. Then we use the formula for electric potential. V is equal to Q over 4 pi epsilon naught R. We substitute the values that we have, we get the value of the potential, electric potential at P due to the 9.8 microcoulomb charge is 8.82 times 10 power 5 volts. Then we have the electric potential at P due to the charge 6.4 microcoulomb you get negative 9.6 times 10 power 5 volts. I told you that we are going to substitute the values of the charges in their signs. Now, since electric potential is a scalar quantity, we shall just find the scalar sum of the electric potential. We add electric potential at P is electric potential due to 6.4 plus that due to 9.8. Then we simply add the two and we get electric potential as 7.8 times 10 power 4 volts. Now, the potential energy due when you bring a charge of negative 6 microcoulomb and place it at oh, sorry, if you bring a charge of 2.5 microcoulomb and place that with P, now the potential energy will be given by the charge that you have brought, which is 2.5 times 10 power negative 6 times the electric potential. You will just go that P and we get the answer as negative 0.195 joules. The figure below shows point charges 44 microcoulomb and negative 22.2 microcoulomb placed at the corners of a square of side 0.5 meters as shown below. Calculate the electric potential at S. Still, electric potential at S is got by electric potential due to P plus potential due to R. So due to P, we substitute in the values with their signs, negative 22.2 microcoulomb times 10 power 9 over 0.5, we get that one, negative 3.99 times 10 power 5 volts. Then potential due to R, again we put the values of the charge the way they are, positive, and we get 7.99 times 10 power 5 volts. Then total electric potential at S, we add the two up, and we get 4.0 times 10 power 5 volts. Now Roman 2, they are asking for the potential energy of 10 microcoulomb charge placed at S. So the potential energy is given by QV. Since it is at S, so we get the charge we are placing at S times the electric potential at S, and we get the answer as 4 joules. Electric potential gradient. Or we want to look for the relationship between electric field intensity E and the PD between the 2 points V. Now, we have to consider 2 points A and B. We have 2 points A and B. As in this figure, we have A here, we have B, which are delta X meters apart. So from point O to point A is X. From point O to point B is X plus delta X. So from A to B is simple delta X. If the potential at A is V, and that the potential at B is V plus delta V, at A is V, at B is V plus delta V, which means the PD between the 2 points is V minus V plus delta V. So PD between A and B is VA minus VB. We substitute to get the VAB as negative delta V. Let's call this one equation 1. Now, the work done to move 1 coulomb charge from A to B, A is here and B is there. If you're moving 1 coulomb charge from A to B, remember that the work done is QV, where V is the potential difference. So we are moving a charge of 1 coulomb, so that work done becomes VAP, which we define as potential difference. But don't forget that VAB again, this same work done can be gotten by force times distance. In this case, our force is between those two charges because you are moving a positive 1 coulomb charge from A to B due to the charge Q. So the charge Q for the force times 1 out of 4 pi epsilon naught R. I'm trying to give you an example using our exact values that we are using, our formula that we are using before. Then R squared, then this is the force times delta X. Now this is Q out of 4 pi epsilon naught R squared times delta X. Now if you look at this first expression here, this first part of the formula for work, this one is electric field intensity, which means our work done actually be electric field intensity delta X. That's what we have here. Now this E delta X is now the same as delta V, as we have shown it up there. But the work done is moving 1 coulomb charge between those 2 points is the potential difference. So when we equate the two, we get the electric field intensity as delta V over delta X. Delta V over delta X is the potential gradient. It's what we call the potential gradient, and it has a negative sign showing that work is done on the particle by the field, on the charged particle by the field. Equipotential surfaces. This is any two-dimensional surface over which the electric potential is constant. If you have a surface whereby the entire electric potential is the same at all points in that field, it means you'll do no work in moving a charge from one point to another on such a surface. And its directional force is always at right angles to the equipotential surface, and it implies that there is no component of electric field inside the surface. And we've got a good example was when we were looking at inside the sphere, the charged hollow sphere. All the points had the same potential. Properties of potential difference, work done, the outside is 0. Then even the electric field intensity along the surfaces is also 0. And the surface is always at right angles to the lines of force. You have examples here about potential surfaces and potential gradient. They are saying calculate the electric field intensity between plates. The lower plate is 0 volts, the upper one is 100 volts. Between them, we have a distance of 10 centimeters, and they are asking us to find the electric intensity, field intensity between the plates. We've just seen that electric field intensity is equal to potential gradient. The negative only shows the direction. So we just substitute delta V, delta X, delta V or dV is the PD. So between the plates, 100 minus 0 is 100. The distance between the two plates, that is delta X, is 0.1. So we get E is 1000 volts per meter. I think we are seeing now why we can give electric field intensity alternative units of volts per meter. Because we have already proved right now that E is negative dV dx. Now dV is PD, which is volts, then dx is in meters. So that's why we can use volts per meter as units for electric field intensity. Then number 2, 2-point charges are 0.1 meters apart. A point charge of 3 times 10 to the power negative 9 coulombs is placed at A. And another point charge, negative 1 times 10 to the power 9 coulombs, is placed at B. You can use the nano instead of 10 to the power negative 9 sometimes. They say 3 nanocoulombs, they mean 3 times 10 to the power negative 9 coulombs. And so one is placed at A of positive 3, the other is placed at B of positive 1. Now, then a straight line joins the 2 points, and along this straight line, between the points A and B, they place they place another charge. No, not placing another charge. They're saying we should find how far this point is, so that at that point the resultant electric potential is zero, or we have zero electric potential at x. And for using the word resultant, because electric potential is a scalar quantity. Now, if we have point A and we have point B, they have charges, as you have seen, 3 nanocoulombs, negative 1 nanocoulombs. Now, there is a point X between the two, A and B, not in the middle, but between the two. We shall establish how far they are from A and B. So, between A and B, the distance is X. Let the distance be X between A and B. Then let it be, that means from A to B it was 0.1 meter. So the remaining, if you have X here, it means you have 0.1, which was the whole distance AB, minus AX, or 0.1 minus X. So since we want the resultant electric potential to be zero at X, we shall first get electric potential at A. Using the formula, this one, we substitute there, and we get 3 times 10 power negative 9 over 4 pi epsilon naught r. Now the r here is AX. Then VB, electric potential at U to B, is negative 1 times 10 power negative 9 over 4 pi epsilon naught 1 minus X. Now, since the electric potential at the point X is 0, then you can just equate the two. VA is equal to VB. When you do so, these ones will cancel with that one, this will cancel with this. You remain with 3 out of X is equal to negative, is equal to, so you're trying to add them up. So this one will be, so this is electric potential due to this, electric potential due to A is this, due to B is that, and since one is positive, one is negative, for us to get to 0, they should be equal in magnitude. So here this side we shall have 1 over 4 pi, 4 pi has already cancelled. Here we have a 1 minus X. Now if we cross multiply, we shall get 3 minus 3x is equal to X. We shall have 4x is equal to, this is 4x is equal to 3, and our x will be, this one was 0.1, this one was 0.1, not 1, 0.1. Oh, sorry, did the wrong substitution here. 0.1, then we shall have 3 times 0.1 minus x is equal to x. 0.3 minus 3x is equal to x. So you'll have 4x being 0.3, and you'll have your x as 0.075 meters. Now, here I've given you an alternative way of doing it, whereby since your charge is negative, this charge is positive. For me to get a zero potential at x, this one will be a positive potential, negative potential. For them to give me 0, they should be equal in magnitude. A positive value plus an equal negative value in terms of magnitude will give you 0. Alternatively, you can just find VA, VB without equating their magnitudes, you add them. That's how it has been done here. After adding, you play with the mathematics. This one is a multiplication sign. You play with the mathematics and you get the value of x as 0.075. We have some exercises here for you to try out. We have from example 1 to example 5. Sorry, from question 1 to question 5. You can pause the video, try them out, and see if you have grasped the concepts in the whole of electrostatics from the beginning up to where we have reached now. These ones cover from the beginning up to where we have reached right now. From the beginning, you can see Coulomb's law along the way coming in. Electric field intensity is there, electric potential is there, then latent energy conductor is there. So you try out and see how you have been able to grasp the content throughout what we have been doing. So this marks the end of electrostatics, and we are going next. In our next future episodes, we shall look at capacitors, then we look at current electricity. Slowly by slowly, we shall finish up the entire electrostatics, capacitors, and current electricity.